Good afternoon, all of you. So, very sorry that we have to join this late, but I had some work last year project in YY is going on, so I was busy there. Very sorry. So, for time being, I have put one quiz. So, kindly attend the quiz. Only 8 people have attended. Why? Why others are not attending? I see how 36 participants are here. Please attend the quiz. So last lecture we have covered limitations of first law. We started the second law. We have seen the heat engine, efficiency of heat engine. And today probably we'll complete the refrigerator, heat pump, etc. etc. Okay. So this quiz is just a reflection of how much you have understood. Okay. So please attend the quiz. I have seen only 8 people have participated. Why others are not participating? Others don't know how to use the mobile, don't know how to click the options. What is the problem? आपल्यात कोणी असे आदिवासी ज्यांना मोबाईलवर कसं टुक करायचं माहित नाही असं कोण आहे काय? Now that you are joining this Zoom meeting, that means you know how to operate mobile. Okay, so participate in quiz also, show how much understanding you have. Give honest answer. Don't search for Google and then come back and don't do such unethical practices. Okay. Yes, 18. Why only 18? 18 is just half of the class. 38 are present and 20. Okay, good. So should I say that 20 people only know whatever we have taken up to this point? Others have not understood. What is the problem? Okay. So first question here it is according to first law. According to first law, machine can have 100% efficiency. So answer is true. First law says that energy cannot be created, cannot be destroyed. It can only change its form from one form to another form. In that case, a machine can have heat as input and he can utilize all the heat to convert it into work. So that way the machine can have 100% efficiency. So it is true. Now second, efficiency of heat engine is net work divided by heat input divided by net work, turbine work divided by heat loss to condenser, and last is heat input to heat loss. Now here we have seen, always remember, whenever a question comes on efficiency, in numerator always will be the objective of that machine. The machine कशासाठी तुम्ही वापरताय त्याचा ऑब्जेक्टिव्ह न्यूमरेटर मध्ये असेल आणि ते ऑब्जेक्टिव्ह मिळवण्यासाठी जे काही एनर्जी तुमची लागली ती तुमची डिनॉमिनेटर मध्ये असेल. ऑलवेज रिमेंबर, कुठेही असेल कुठलाही सब्जेक्ट असेल. Now in this case heat engine is used to do some work, so net work will be in the numerator and heat input it will be in the denominator. So A is the correct option. Last is first law is directionless law. So first law does not give you direction whether this process is possible or not. म्हणजे एखाद्या हॉट कप ऑफ कॉफी मधून हीट लॉस होणे हे समजू शकतो, पण ती लॉस झालेली हीट परत कॉफीला देणे इट इज इलॉजिकल. सो but first law says that it is possible. First law is not concerned with direction of the process, so it is a directional law. Correct answer is true. So most of the students have failed. Last third question, 14 students have failed. First law, directional law, that is correct. And again, the numbers are not satisfactory. Even for the first question, the 11 people have given wrong answer. Okay, so don't do such thing. I will share the results so that you will come to know. I hope everybody is able to see the results. Okay. Second answer is A, net work divided by heat input. The objective will be in the numerator and the energy input will be in the denominator. So net work divided by heat input. Now we'll start today's lecture. We'll first cover whatever we have learned from the previous lecture. Then we can continue. So first we'll see what was the problem with first law and all that. Then we can continue. Yes. Am I audible? Yes. First question answer explain. Okay. So first question was, by first law of machine क्या 100% efficiency. आता 100% efficiency म्हणजे काय? जेवढं इनपुट येते तेवढंच आउटपुट तुम्हाला मिळते. ठीक आहे. फर्स्ट लॉ काय म्हणतं की मला एनर्जी कुठं जाते कशी जाते याची काय देणं घेणं नाही. मला काय फक्त पाहिजे की एनर्जी, टोटल क्वांटिटी ऑफ एनर्जी रिमेन्स कॉन्स्टंट. ठीक आहे. म्हणजे सपोज एक मशीन आहे, त्याने घेताना 50 किलोवॅटची एनर्जी इनपुट घेतली आणि त्याने 50 किलोवॅटचं वर्क केलं. तर या केसमध्ये काय झालं? वर्क कन्वर्जन झालं. फर्स्ट लॉ इज सॅटिस्फाईड. सो बाय फर्स्ट लॉ that machine, what will the efficiency of machine? 50 divided 50, 1 is means 100%. Efficiency of that machine will be 100%. First law is satisfied. But in actually it does not happen. जर तुम्ही 50 किलोवॅट एनर्जी घेत असाल तर त्यातलं 30 किलोवॅटच एनर्जी तुम्ही युटिलाइज करू शकता फॉर युजफुल वर्क. 20 किलोवॅट ऑफ एनर्जी इज वेस्टेड. सो the first law fails here. So but by first law a machine can have 100% efficiency. Okay. So now I'll share the screen and start the presentation. I hope I'm able to. Okay, what is this? Screen here. Move to slide. Previous page show. Okay. Arrow highlighter. Ballpoint pen. Okay. Highlighter. Okay. So we started last lecture with the limitations of first law. Now by first law we have seen some new examples. So this was one of the examples. This is the example of heat loss by cup of tea. Now this is cup of tea. Let us say it is very hot. Heat loss by this cup of tea to the surrounding, that is possible. ह्याच्यातून बाहेर heat transfer होणे हे आपण समजू शकतो. ठीक आहे. But transferring heat from the surrounding, म्हणजे ही हीट जी लॉस झाली ऑलरेडी एन्व्हायरमेंट मध्ये, एखादा गॅस आलाय, एअर आली, ती हीट त्याने ऑब्झर्व केली आणि ती एअर निघून गेली, कुठे गेली आपल्याला माहित पण नाही. आता परत तीच एअर शोधायची, कुठल्या एअरनं हीट नेली त्या एअरला शोधून आणायचं, त्याच्यातली हीट काढून घ्यायची परत कपला द्यायची. दिस इज नॉट पॉसिबल. अगेन सप्लाइंग दॅट हीट बॅक टू द कप ऑफ टी, इट इज नॉट पॉसिबल. ओके. दुसरा वे काय आहे तर यू अगेन स्टार्ट द स्टोव्हवर परत तुम्ही चहा ठेवा, तुमचा चहा गरम होईल. बट दिस इज different energy. This is, let us say, Q2. This is new energy, or this is different energy we are supplying. But the whatever heat loss supplied by the lost by the cup of tea, we cannot supply it back to the cup of tea from the surrounding. म्हणजे हे कशासाठी सारखं झालं तर मी जर रोबोट पिक्चर बघितला असेल, रोबोट पिक्चर मध्ये ऐश्वर्या रायला डास चावतो. ते रोबोट येणं येताना म्हणतं की काय झालं तुला, ती म्हणजे डास चावला. पण तो डास शोधत जातो आणि त्या डासांच्या गुणकेतनं त्या डासाला शोधून आणतो आणि त्याला सॉरी म्हणालो. हे त्यासारखं झालं, विच इज नॉट पॉसिबल अँड विच इज नॉट लॉजिकल. नेक्स्ट हियर वी हॅव अनदर एक्झाम्पल इज, एक इलेक्ट्रिक वायर आहे. ठीक आहे. ज्यावेळेस तुम्ही यातून इलेक्ट्रिसिटी पास करता त्यावेळेस काय होणार आहे, इथून थोडं हीट विल बी जनरेटेड, यातून थोडी हीट जनरेट होईल. ठीक आहे. आता याचे वेगवेगळे ऍप्लिकेशन्स आहेत. तुमच्या घरात जसं गिझर आहे, तर गिझर मध्ये हे देखील ही हिटिंग कॉइल असते, ते हीट वापरून तुम्ही पाणी गरम करता. बट उलट होऊ शकतंय काय, म्हणजे गरम पाण्यातून परत तुम्ही ही हीट इलेक्ट्रिक वायरला सप्लाय करणार आणि ह्याच्यातून इलेक्ट्रिसिटी जनरेट होणार, असं होऊ शकतं का? तर असं होऊ शकत नाही. बट फर्स्ट लॉ इज सॅटिस्फाईड अँड इट इज नॉट प्रॅक्टिकल ऑल्सो. म्हणजे ही जी प्रोसेस आहे परत सप्लाय करणे, हे फर्स्ट लॉ नुसार सॅटिस्फाय होऊ शकतं, एनर्जी कन्वर्जन होऊ शकतं, बट प्रॅक्टिकली इट इज नॉट पॉसिबल. Okay. So heating a room by electric heater by passing electric current through resistor, electric energy supplied to the heater is equal to energy transferred to the surrounding. So first law is satisfied. Energy conversion takes place. Total quantity of energy is constant. However, converse is not true. Transferring heat to the wire, equivalent amount of electric energy is generated. This is not possible. Okay. Still, first law is satisfied because first law is considered with only total quantity of energy, whether it is conserved or not. The third example was this one. So there is a weight attached to a shaft. This shaft has some Pelton wheels are there. This is inside a closed system. It has some fluid is there inside this, and its function is to steer that fluid. आता पहिल्यांदा काय होणार आहे तर हे वेट आपोआप बाय ग्रॅव्हिटी खाली पडेल, शाफ्ट रोटेट होईल तुमचा, आणि रोटेट झाल्यामुळे हे ब्लेड्स देखील फिरतील आणि ब्लेड्स मधून थोडीशी हीट ट्रान्सफर होईल कशाला, फ्लुइडला. सो दॅट इज अंडरस्टूड. बट इफ रिव्हर्स इज पॉसिबल, इज रिव्हर्स पॉसिबल, परत ह्या फ्लुइड मधून परत त्या व्हीलला तुम्ही हीट देणार आणि मग हा शाफ्ट उलटा फिरणार, उलटा फिरल्यानंतर हेड वेट परत जाणार. दिस इज नॉट प्रॅक्टिकली पॉसिबल, बट फर्स्ट लॉ इज सॅटिस्फाइड. So that was the limitations of first law. It is a directionless law. It does not give you the quantity, or it is concerned only with the quantity. It does not give you the quality of the work that can be produced. For that purpose, we have second law of thermodynamics. Okay. So it asset energy adds, it has quantity as well as quality. Okay. It is also concerned with degree of degradation of energy. Okay. डिग्री ऑफ डिग्रेडेशन म्हणजे काय, जर तुम्ही सकाळी उठता, मग व्यवस्थित व्यायाम करता, योगासन करता, नाश्ता करता, दणकून खाता, तर सुरुवातीला तुम्हाला काम करायला फार जोश असतो. म्हणजे काय असतं तर तुमचं युजफुल पोटेन्शियल जास्त असतं, जास्त वर्क करायचं तुमचं पोटेन्शियल असतं सकाळी. तसंच तुम्ही दिवसभर काम करता, संध्याकाळी तुम्ही एकदम कंटाळलेलं असतं. म्हणजे काय होतं, तुमचं वर्क पोटेन्शियल संध्याकाळी कमी होतं. सो सेकंड लॉ ऑल्सो गिव्स यू द डिग्री ऑफ डिग्रेडेशन ऑफ एनर्जी. इट ऑल्सो टेल्स यू how much amount of work is actually useful. Okay. So last lecture we have seen heat engines. We have seen how to calculate their efficiency, right? Efficiency's formula was net work output divided by total heat input. One of the examples we have taken, that is of the thermal power plant. आता हे चार मेन कंपोनेंट आहे, लक्षात ठेवा thermal power plant चे. Boiler, turbine, condenser, and pump. These are the major four components of a thermal power plant station. Okay. ह्यात होतं काय तर आपण हीट सप्लाय करतो कुठं, बॉयलर मध्ये. म्हणजे आपण काय करतो तर कोळसा असतो, तुम्ही जर बघितलं असेल किंवा तुम्ही कुठं ऐकलं असेल, एक मोठा थर्मल पॉवर प्लांट स्टेशन असतं, त्याच्यामध्ये आत यायला रेल्वेचे ट्रॅक्स असतात. ठीक आहे, जे सोलापूर किंवा ह्या एरियात आहेत, होटगी रोड या एरियात, त्यांनी पुढे जाऊन कधी बघितलं तुम्हाला कळेल की त्या पॉवर प्लांटच्या आत जायला रेल्वेचे ट्रॅक्स असतात. आता हे कशासाठी असतात तर ट्रेन मधून कोळसा येतो. म्हणजे ह्या ज्या कोळशाच्या खाणी आहेत, चंद्रपूर किंवा इकडं तिकडं या ठिकाणून काय होतं, मोठ्या प्रमाणात कोळसा हा ट्रान्सफर केला जातो बाय ट्रेन. आता हा कोळसा काय करतो, बॉयलर मध्ये टाकला असतो आणि देर इज अ फर्नेस. Inside the furnace, the burning of coal takes place. Heat is supplied to the water, which is passing through the tubes. The water चं परत काय होतं, कन्वर्जन स्टीम मध्ये होतं. This high pressure, high powered, high temperature steam is passed to turbine. Turbine मध्ये काय होतं, ती स्टीम टर्बाइनच्या ब्लेड्स वर पडते, त्यामुळे टर्बाइनचा शाफ्ट रोटेट होतो. This shaft is connected with generator shaft, and in generator, electricity is generated. Now at the output or outlet of turbine, we have low pressure, low temperature air, which is passed to the condenser. It is converted into water. This water is again pumped to the boiler pressure with the help of a pump. Okay. So here in this case, the source is boiler, sink is condenser, work producing device or the heat engine is a turbine. Okay. So that term also we studied in the last lecture. Thermal energy reservoirs म्हणजे असे एनर्जी रिझर्वायर त्यांच्या टेम्परेचर मध्ये काहीही फरक पडत नाही. त्यांना तुम्ही हीट द्या, त्यांच्यातून हीट काढा, त्यांच्या टेम्परेचर मध्ये काहीही इफेक्ट होत नाही. जसं की सन, सूर्याला तुम्ही किती पण हीट द्या, त्याच्यातून किती पण हीट काढून घ्या, त्याचं टेम्परेचर ऑलमोस्ट रिमेन्स कॉन्स्टंट. फॉर एक्झाम्पल ओशन मध्ये तुम्ही किती हीट डंप करा, किती पण हीट त्यातून काढून घ्या, the average temperature somewhat remains constant. So these are called as thermal energy reservoirs. And the thermal energy reservoir which is at higher temperature, it is called as source. Thermal energy reservoir which is at low temperature, it is called as sink. Okay. So the formula here it is. This is a notation for the efficiency. It is generally written as like this. हत्तीचे सोंड असते तसं थोडं काढलं जातं. NTH. TH stands for thermal. This is stand for efficiency. So this is stand for thermal efficiency. Thermal efficiency is equal to net work output divided by heat input. Net work output can be also be written as QH minus QL. So finally, this formula reduces to 1 minus QL divided by QH. Okay. So this we have seen in last lecture. Now, today's lecture is about two very important statements which are called as Kelvin-Plank statement and second is Claussius statement. Okay. So in last lecture we have seen there is a concept called PMM, perpetual motion machine of first kind. The perpetual motion machine of first kind काय असते, तर ती फक्त एनर्जी घेते, ती फक्त वर्क करते कोणतंही हीट इनपुट न देता. म्हणजे असं म्हणता येईल की तुम्हाला मी काहीच खायला देणार नाही, तुम्हाला घरचे किंवा मेस मधलं तुम्ही काहीच खाणार नाही, पण तुम्हाला काही भूक न लागता तुम्ही काम करू शकता. सो दॅट मीन्स यू आर डुईंग वर्क विदाउट एनी इनपुट. So that is called as perpetual motion machine of first kind. Now by first law it is not possible, but because first law says that there should be an energy conversion. So in that case, first law says that PMM, that is perpetual motion machine of first kind, it is not possible. So by first law, perpetual motion machine of second kind is possible. Second kind आता कशी असते, त्यामध्ये एक heat input असतो, एक work output असतो, all the heat is converted into work. So PMM SK is the machine with 100% efficiency. आणि नंतर येतो सेकंड लॉ. सेकंड लॉ मधलं केल्विन प्लँक स्टेटमेंट काय म्हणतं की मशीन कॅनॉट हॅव 100% इफिशियन्सी. म्हणजे जेवढं हीट इनपुट आहे तेवढंच तुम्ही वर्क करू शकत नाही. देअर ऑलवेज विल बी सम हीट लॉस. ओके, देअर ऑलवेज विल बी सम हीट लॉस. सो दॅट इज द स्टेटमेंट गिवन बाय केल्विन प्लँक. सो विल सी. So what you see on the screen, this is a PMM SK, perpetual motion machine of second kind. It is receiving 100 kilowatt of energy and all that heat is converted into work. So it is having, what will the efficiency in this case? Efficiency or the thermal efficiency in this case will be what? If I write down this equal to net work done divided by QH, very sorry for this. So in this case, this will be equal to 100 divided by 100, and this will be equal to 1. So that means this is efficiency in this case is 100%. 100%. So this is a machine. What I am saying is PMM SK, machine with 100% efficiency. By first law, it is possible to have PMM-SK, but second law in that Kelvin-Planck statement says that PMM-SK is not possible. We'll see the statement. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work. That means you cannot convert all the heat input into useful work. Alternatively, no heat engine can have a thermal efficiency of 100%. Okay, write down this statement, Kelvin-Planck statement, and draw that figure also. Very, very important statement. So yesterday there was a external viva for last year mechanical engineering students. In that also I had asked what is Kelvin-Planck statement, what is Claussius statement. Some students were able to answer, some students were not able to answer, right? Because this is a basis for the refrigeration. Clausius statement is a basis for refrigeration. Kelvin-Planck statement is the basis for heat engines. Completed? Yes, completed. Okay. Next we'll see refrigerator and heat pump. Okay. So now up to this point we have seen heat engine which receives heat from source. It does some work and rejects some amount of heat into the sink. Okay. Now next is refrigerator and heat pump. Now in this case the flow of energy is reversed. That means naturally the heat always flows from higher temperature to lower temperature. But in case you want to transfer heat from low temperature to the higher temperature, you will need a refrigerator. Okay, so understand what is the difference between heat engine and refrigerator. In heat engine, the flow of energy or the heat is natural, that is from higher temperature source to the lower temperature sink. In refrigerator, the flow is reverse. Heat is extracted from low temperature reservoir, that is sink, and it is transferred, and heat is transferred to higher temperature reservoir, that is source. Okay. Now, being a diploma students, you are aware of the VCRS cycle, vapor compression, refrigeration cycle. It contains 4 major components: evaporator, compressor, condenser, and expansion valve. In this case, the sink, which is at low temperature, is evaporator and the source is condenser. So in this case, heat is extracted in the evaporator and heat is supplied in the condenser. Okay. So for this, we have Claussius statement which says that in order to transfer the heat from lower temperature reservoir to the higher temperature reservoir, we need some external work. Without external work, you cannot transfer heat from low temperature to high temperature. So that is a statement for Clausius statement. Okay. So heat is always transferred from high temperature to low temperature region. The reverse process cannot occur on itself. Transfer of heat from low temperature region to high temperature one requires special devices known as refrigerators. Okay. So refrigerator heat pump. This is a classic diagram for refrigerator heat pump. Now, what is the difference between refrigerator and heat pump? Can anybody tell? So I will tell for refrigerator and heat pump, this diagram is same. That is, there is a sink, there is a source, there is this machine is there. It will extract the heat from sink and it will supply some heat to the source, and there will be some work input. Okay. So this diagram is same for refrigerator and heat pump. What is the difference between refrigerator and heat pump? Can anybody tell? Does anybody remember from their diploma what is the difference between refrigerator and heat pump? Yes, does anybody remember? Yes, does anybody remember? What is the difference between refrigerator and heat pump? Yes. Okay, I see no responses in the chat box. Okay, I hope that many of students have forgotten. So the major difference between refrigerator and heat pump. Okay, I will take, please listen carefully. In refrigerator, our objective is to maintain the low temperature reservoir at low temperatures than surrounding. Okay, the objective काय आहे? हे जे आहे sink or the low temperature reservoir, we want to maintain it at a temperature lower than surrounding. So this is for refrigerator. Heat pump मध्ये काय होत असते? We want to maintain the high temperature reservoir at higher temperatures than surrounding. म्हणजे ह्यामध्ये ऑब्जेक्टिव्ह सोर्स असतो हीट पंप मध्ये, रेफ्रिजरेटर मध्ये ऑब्जेक्टिव्ह असतो सेम. आपल्या रेफ्रिजरेटर मध्ये हे लो टेम्परेचरला ठेवायचं आहे, हीट पंप मध्ये आपल्याला हे हायर टेम्परेचर मध्ये ठेवायचं आहे. ठीक आहे. So Aditi has tried her luck in refrigerator energy transfer from low temperature to high temperature. No, in both refrigerator and heat pump, In both the cases, energy transfer takes place from low temperature to high temperature reservoir. But the difference is in objectives. Refrigeratorचं ऑब्जेक्टिव्ह असतं की हे लो टेम्परेचर ठेवणे सिंक. हीट पंपचं ऑब्जेक्टिव्ह असतं सोर्स हाय टेम्परेचरला ठेवणे. Okay, I hope I have cleared your doubt. So by this definition, we'll move towards COP. COP stands for coefficient of performance. Now for heat engine, we have term called as thermal efficiency, but for refrigerator and heat pump, we have a term which is called as COP, coefficient of performance. Okay. So efficiency of refrigerator is expressed in terms of coefficient of performance, COPR. COP is equal to desired output divided by required input. That will be the COP. Now, I will ask to you, what will be the desired output in case of refrigerator and what will be the desired output in the case of heat pump? Can anybody tell? The required input will be same, that is W net in, but the desired output will change. Can anybody guess what will be the desired output for refrigerator and what will be the desired output for the heat pump? Right? You can tell in the terms of QL and QH. Okay, I repeat my question. So see here, COP formula is given, desired output divided by required input. Required input in the case of refrigerator and heat pump will be same, that is W net in. This will be common, but the numerator will change, right? It will be QL or it will be QH. Now for refrigerator, what should we take in the numerator? Should we take QL or should we take QH? Yes, Akanksha, good. Heat pump, in a heat pump QL. Okay. And in heat pump QL. Okay. Akanksha, your answer is related to heat pump or refrigerator. Sudhir, is your answer related to refrigerator or heat pump? Akanksha is saying refrigerator. Okay. So see, Tejal, your answer is incorrect. What I'm saying is that objective of refrigerator is to maintain the lower temperature reservoir, that is evaporator at low temperature. So our output will be QL. ठीक आहे, म्हणजे तुम्हाला COP of refrigerator लिहायची असेल तर न्यूमरेटर मध्ये QL येईल. If you want to write down the COP of heat pump, the heat pump's objective काय? To maintain this high temperature reservoir at high temperature. त्याच्या relevant term काय आहे? QH. So here it will be QH divided by W in. Okay, so that's the formula for heat pump. Always look for objective. So the first law of thermodynamics gives net work input will be equal to QH minus QL. So COP can also be written as like this. So this net work output input can be written as QH minus QL. So if you divide both numerator and denominator, here it will be 1, here it will be QH divided by QL minus 1. So write down this formula, COP of refrigerator. COP of refrigerator. Next. So thus COP can be greater than 1. So always remember COP is always greater than 1. COP can never be less than 1. And thermal efficiency is always less than 1. COP is always greater than 1. For heat pump, COP is expressed as COPH pump. So see here, desired output divided by work input, desired output will be QH. Why QH? Because we want to maintain the high temperature reservoir at higher temperature. So here QH will be our output. So QH divided by W. Okay. Now there is very special relation between COP of heat pump and COP of refrigerator. This is the question of MCQ. Please remember. Okay, I will tell you the relation. COP of heat pump is always equal to COP of refrigerator plus 1. Okay, this is a MCQ question, and there will be some numericals if possible will be asked. COP of heat pump will be always equal to COP of refrigerator प्लस 1. असं समजा की सीओपी ऑफ हीट पंप हा मोठा भाव आहे, सीओपी ऑफ रेफ्रिजरेटर हा छोटा भाव आहे, आणि त्यांच्यातलं रिलेशन असं आहे की सीओपी ऑफ रेफ्रिजरेटर प्लस 1 इज इक्वल टू सीओपी ऑफ हीट पंप. सीओपी हीट पंप मोठा भाव, लहान भाव सीओपी रेफ्रिजरेटर पेक्षा 1 वर्षांनी मोठा आहे. ओके, सो ऑलवेज रिमेंबर दिस रिलेशन. Okay. So here comes the Claussius statement. We study. It is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a lower temperature body to higher temperature body. So it says that if there is a machine, so this machine is called as converse of PMM-SK. Okay. In Kelvin-Plank statement, we have seen PMM-SK, perpetual motion machine of second kind. And what you see on the screen, this is a converse. This is a converse of PMM-SK. PMM, perpetual motion machine of second kind. So what is converse of PMM-SK? So it is a refrigerator which will absorb the heat from sink. It will supply the heat to the source without any heat or work input, or without any input. It will transfer heat from lower temperature reservoir to higher temperature reservoir. And Claussius statement says it is not possible. Why it is not possible? Because see, naturally, if you see, it always flows from higher temperature to low temperature, right? But in order to transport heat from low temperature to the higher temperature, it cannot take place on its own. It needs some external work. And external work can be supplied in the form of pump or compressor, etc., etc. General refrigerator, we are using compressor. Okay. Alternately, no refrigerator can operate unless its compressor is supplied with external power source. Okay. So write down this. This is very important. Clausius statement. It forms the basis for the refrigerators. Yes, completed. Draw the diagram also. This diagram is converse with PMM-SK, and Clausius statement says that converse of PMM-SK is not possible. That is, we need some external work in order to transfer the heat from low temperature to high temperature. आता हे पीपीटी बघताना किंवा मी बोलताना सगळं इझी वाटतं तुम्हाला, हा असं होऊ शकते असं तसं, बट गिव्ह युअर थॉट्स. So do your self study also, do read the notes or the literature, do your study also. When you will do your self study, that time only you will understand the concepts. Okay. So हे फार कॉमन आम्ही मेंटॅलिटी बघतो स्टुडंटची. इन क्लासेस दे थिंक दॅट एव्हरीथिंग इज पॉसिबल आणि सगळं समजते असताना होतं. आणि ज्यावेळेस ते ऍक्च्युअल मध्ये बुक्स ओपन करतात, नोट्स ओपन करतात, त्या केसमध्ये त्यांना असं वाटतं की काहीच नाही, म्हणजे काहीच आपल्याला काहीच समजलं नाही, सगळं डोक्यावरून गेलं. सो इट हॅपन्स ऑफनली. ओके, इट हॅपन्स विथ टॅलेंटेड स्टुडंट्स, ऍव्हरेज स्टुडंट, एव्हरी टाइप ऑफ स्टुडंट दिस हॅपन्स इन क्लास. असं वाटतं की सगळं समजत चाललंय, सगळं सोपंच आहे, बट वेन दे ओपन द बुक्स दे फाइंड इट डिफिकल्ट. ओके, सो डू युअर सेल्फ स्टडी ऑल्सो रेग्युलरली, so that at the time of examination your head will not burst. Now next is a very interesting finding from the research it is obtained, that is a violation. Suppose there is a Kelvin machine, there is a heat engine which follows Kelvin-Plank statement. There is a refrigerator which follows the Kelvin-Plank statement. So there is a figure. Okay, in this case there is a source is there, and there is a heat engine is there. It receives the amount of QH and it violates the second law of the Kelvin-Planck statement. How it violates? It converts all the heat into net work and the heat loss is zero. So it has violated the Kelvin-Planck statement. Now all that work output will be the work input to the refrigerator. Here it is extracting the amount of heat QL and it is transferring amount QH plus QL. Okay. Now when you take the equivalent of this system, complex system, this will look like this. And this is nothing but the converse PMMSK. That is, there is a refrigerator, it takes the heat from sink, supplies same amount of heat to the source because there is no work input. It is not taking any work input. So it says that violation of Kelvin-Planck statement results in violation of Claussius statement. Converse is also true. That means violation of Claussius statement will be violation of Kelvin-Planck statement. Okay. Once again, I will explain. There is a source, there is a sink. त्यामध्ये तुम्ही समजा एक हीट इंजिन ऑपरेट करत असाल आणि दॅट हीट इंजिन इज व्हायोलेटिंग द सेकंड लॉ, आणि त्याच सोर्स अँड सिंक मध्ये तुम्ही एखादा रेफ्रिजरेटर ऑपरेट केला, सो डेफिनेटली इट विल ऑल्सो व्हायोलेट द सेकंड लॉ. त्यामुळे केल्विन प्लॅंक स्टेटमेंट जर व्हायोलेट होत असेल तर त्या कंडिशन मध्ये क्लॉसियस स्टेटमेंट देखील व्हायोलेट होते. व्हायोलेट होते म्हणजे इट इज नॉट ओबेइंग द सेकंड लॉ ऑफ थर्मोडायनामिक्स. So this is a okay. Now before moving to the entropy, I want to make sure everybody has understood what is second law, what is Kelvin-Planck statement, what is Clausius statement. Yes, anybody having any doubt up to this point? Anybody is having any doubt up to this point? Okay. So now I will connect the tab. Also, a lot of writing has to be done for the entropy. Okay. Now, before going to the entropy, we'll study Carnot cycle. Okay, we'll study Carnot cycle. I will add a slide here. Wait, before entropy, we'll study Carnot cycle. Anybody know what is Carnot cycle? बोले चलो Carnot cycle. Does anybody know what is Carnot cycle? Is my screen visible to all of you? Yes, is my screen visible? Yes. Is my screen visible? Okay, okay. Thank you. So, what is Carnot cycle, right? Carnot cycle is an ideal cycle for a heat engine. It is an ideal cycle for heat engines. Okay. All the processes in Carnot cycle are reversible. All processes are reversible. That means they can be reversed on itself. We don't need external power to reverse the direction of the process. Okay. It has two isothermal processes and two isentropic processes. It is a cycle with highest efficiency or highest thermal efficiency. Okay, I will draw the Carnot cycle. Please draw along with me. So we'll draw in two steps. First, we'll draw on temperature versus entropy. Second, we can draw it on pressure versus. Okay. So first of all, write down this introduction part. This all what I have written here. Please write it down. Write down this part also. Okay. So first graph here it is temperature versus entropy graph. There are two isothermal processes. So that means this will be, there will be two horizontal lines. And there are two isentropic processes. That means there will be two vertical lines. LDM it has 1 to 2 to 3 to 4. Okay. So 1 to 2 is a isothermal expansion process. Sorry, isothermal heat addition process. That means heat is added 1 to 2. 2 to 3 is a isentropic expansion. Isentropic expansion. and some work is produced, work out. 3 to 4 is isothermal heat rejection. That means some amount of heat is rejected. 4 to 1 is a isentropic compression. That means some heat, external work is required, W in. If I want to show this process on PV, it will look something like this. Okay, 1 to 2 to 3 to 4. 1 to 2 is again isothermal, 2 to 3 is isentropic, 3 to 4 is isothermal, and 4 to 1 is a isentropic. Okay. Now, in this case, if you want to calculate thermal efficiency, what will the formula? Work net divided by QH. What will the work net? Will be equal to W out minus W in, right? Or I can write this also as QH minus QL divided by QH. Or I can write this as a 1 minus QL divided by QH. Now, very important feature of the Carnot cycle is I can write down the ratio of QL QH as equal to TL divided by TH. What is TL? TL is sink temperature, TH is source temperature. So here this lower temperature is TL and higher temperature is TH. So the formula of thermal efficiency reduces to 1 minus TL by TH. So this is the formula applicable to only heat engine working on Carnot cycle. Working on Carnot cycle. So for any heat engine, this formula is applicable, but for the heat engines working on Carnot cycle, this formula is added advantage. We can use both the formulas. Okay. Okay. Right. Now, there is a term which is called as second law efficiency, which is called as second law efficiency. Second law efficiency, which is also written, the symbol is N and Roman 2. This is called as second law efficiency. So what is second law efficiency? See, for a heat engine, the formula is 1 minus QL by QH. So you calculate this thermal efficiency, and for heat engine working on Carnot cycle, the efficiency formula, it is also written as NTH comma reversible, because all the processes are reversible. NTH reversible is, we all know, 1 minus TL by TH. And second law efficiency is nothing but the ratio of NTH divided by NTH reversible. That means first you have to calculate the thermal efficiency of the given heat engine or the heat engine under consideration. Then you have to calculate the Carnot efficiency for the same sink and source temperatures. And if you take the ratio of these two, you will get second law efficiency. Second law efficiency थोडक्यात तुम्हाला सांगतं की तुमचं जे heat engine आहे, how close it is to the Carnot cycle. म्हणजे तुमचं जे हिट इंजिन आहे, समजा तुम्ही उद्या एखादी कार तयार केली किंवा एखादं हिट इंजिन थर्मल पॉवर प्लांट तुम्ही उभा केलं, तर तुम्हाला बघायचं की मॅक्सिमम एफिशियन्सी जी मिळते कुठून मिळते आपल्याला? मॅक्सिमम एफिशियन्सी कॅर्नॉट सायकलला मिळते. ती जी बॅक्सन इफिशियन्सी आहे आणि माझ्या आत्ताच्या इफिशियन्सी किती गॅप आहे. सो दॅट इज टोल्ड बाय सेकंड लॉ इफिशियन्सी. सिम्पली यू टेक द रेशो. तो जर जेवढा 1 च्या जवळ असेल दॅट मीन्स वी आर नियर टू मॅक्सिमम इफिशियन्सी. तो जर समजा 0.5 असेल तर आपण म्हणू शकतो की अजून आपल्याला 50% इफिशियन्सी आपली वाढवावं लागेल. ठीक आहे. सो दॅट इज सेकंड लॉ इफिशियन्सी. Now next comes, now this is about heat engine. Heat engine la ठीक है, Carnot cycle. What is about refrigerators and heat pumps? So for refrigerators and heat pumps, we have a reverse Carnot cycle, right? So as all the processes in the Carnot cycle are reversible, we can change the direction, right? So if I change the direction of this, so let me write down here title reverse Carnot cycle. Sorry. Okay. Reverse Carnot cycle. See, so this is a Carnot cycle. All the processes are reversible. So that means its direction can be changed. So I will reverse the direction of all these processes. So see what I will get here. So this is again temperature versus enthalpy. This is again pressure versus volume. Okay. So simply I will change the direction. So direction will be now will be like this, and this. So you can cross check. Initially direction was in this direction, process was taking place. Now the direction is reversed. So the name comes reverse Carnot cycle. So again, let us say this is one to 2 to 3 to 4. Again, in this case, you will observe similar behavior. 1 to 2 to 3 to 4 to 4. Okay. What is happening in this case? 4 to 1. 4 to 1 is a isothermal heat extraction process. So heat is extracted from steam. 1 to 2 is an isentropic compression. So it needs some work input. 2 to 3 is the isothermal heat rejection process. So that is, it will reject some heat into the atmosphere, QH. And 3 to 4 is isentropic expansion process. So that means it will do some work or some work will be lost. Work is lost in the 3 to 4 process. Similarly, here we have PV diagram, here it is TS diagram. Now, normally, what is COP of a refrigerator? COP of any refrigerator is equal to QL divided by W in, or we write it as a QL divided by QH. So wait, QH minus QL. Now, for refrigerator working on reverse Carnot cycle, the COP is written as COP of R, comma, reversible, so equal to. So here it can also be simplified as 1. So I will divide the numerator and denominator by QL. So this will become QH by QL minus 1. So for refrigerator working on reverse Carnot cycle, we have added advantage that QH divided by QL will be equal to TH divided by TL. So this can also be written as 1 divided by TH divided by TL minus 1, or I can write this as a TL divided by TH minus TL. Okay. So this is a COP for any refrigerator in the world. This is a COP for the refrigerator working on reverse Carnot cycle. That means this will give you maximum COP. This will give you maximum COP. And again, in second law efficiency, you can take the ratio of these two. It will give second law COP. Okay, what is second law COP? So COP refrigerator, that is by second law, will be equal to COP of a refrigerator divided by COP of a refrigerator working on reverse Carnot cycle. So that will be second law COP. Similarly, you can go with the heat pump also. Any doubt up to this point? Any doubt up to this point? Okay. Yes, any doubt? Okay. Now I will take some numericals. We'll solve some numericals so that your understanding will be more clear. So I think we have one numerical already here. Okay. We'll solve this numerical. Shall we solve? Okay. So here is the numerical on your screen. A Carnot cycle is having efficiency of say 0.75. If the temperature of the high temperature reservoir is 727 degrees Celsius, what is the temperature of low temperature reservoir? Okay. So for this, we'll require the formula of thermal efficiency for Carnot cycle. Always convert temperatures in Kelvin. So I'll give you 1 minute. Those who have understood the problem, they can try their luck. And after 1 minute, I will solve the problem for others. Okay. So see here, the given data. So in the given, I will draw the heat engine. What is the schematic for heat engine? There is a sink is there, TH. Then for that heat engine is connected, it will take some amount of QH. It will do some work, that is W. It will lose some heat, that is QL, to the sink at TL. Now here the high temperature is given, that is 727 degrees Celsius. The efficiency of the cycle is given, that is NTH is equal to 0.75. You need to calculate what is TL. Okay. Now here TH is equal to 727 degrees Celsius. I want to convert in Kelvin. So 727 plus 273. This will give you how much? 800. This will be 1000 Kelvin. Okay. Now what is the formula for a cycle working on Carnot? And TH reversible will be equal to 1 minus TL divided by TH. Here it is given as 0.75 will be equal to 1 minus TL is unknown divided by 1000 Kelvin. So calculate TL. How to calculate? So what I will do, I will take T this term on this side and 0.75 this side. So this will become TL divided by, TL divided by 1000 will be equal to 1 plus, not my 1 plus 1 minus 0.75 will be equal to 0.25. So TL will be equal to, this 1000 will go on this side. This will become 1000 into 0.25. This will become 250 Kelvin. Anybody is successful in calculating this? Option number D. No, 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 no. Yes, wait. Don't rush. So take care. Whoever has posted option number D, please take care. It is not option number D. Aditi, don't rush to answer. Now we have calculated TLS 250. Convert this into Kelvin. How to convert? This will be 250 minus 273. So this will give you minus 23 degrees Celsius. So correct answer here it is minus 23 degrees Celsius. See, you might have drawn this diagram, you might have solved, you might have reached to up to this stage. Okay, this is your hard work. Don't waste your hard work by selecting wrong option. Okay. ह्याच्यापर्यंत तुम्ही एवढे कष्ट घेतले 250 केल्विन आले त्यानंतर गडबडीत तुम्ही 250 डिग्री सेल्सिअसला सिलेक्ट करू नका कन्वर्ट केल्विन इनटू डिग्री सेल्सिअस it is minus 23 degrees Celsius. Yes, Aditi, understood? Okay, so option number C is correct. So so I don't have actually more numericals to give you. Okay. Okay, very important numerical we'll take now and then we'll stop. Those who did not write down this numerical. Okay. Any doubt? Yes. Okay. So we'll move to a second very important numerical here. So it says for two cycles coupled in series, the topping cycle has efficiency of 30%, the bottoming cycle has an efficiency of 20%. The overall combined cycle efficiency is, see, it is new to you. I will explain what is happening here. So there are two cycles in series. Okay. So there are two cycles in series. So first cycle I will draw here. So this is the first cycle. Right. This is a heat engine one. Okay. So it has heat source temperature H1, it has QH1, it will do some work W1, then it has QL1, and here we have TL1. Now there is another cycle which considers this TL1 as its source temperature. So that means there is another cycle at the bottom. There is another heat engine 2. Then it has some other thing. So here TL1 is TH2. Here again QH2, W2. Again here you have QL2 and TL2. So here TL1 is equal to TH2. Okay. Now the efficiencies of these two cycles are given. याचा अर्थ काय आहे थोडक्यात मी सांगतो की एक पहिलं हीट इंजिन आहे हीट इंजिन 1 ते QH अमाउंट ऑफ वर्क हीट घेते W1 अमाउंट ऑफ वर्क करते आणि QL1 अमाउंट ऑफ एनर्जी लॉस करते सिंक मध्ये. आता ह्याचा जो सिंक आहे तो नेक्स्ट सायकलचा सोर्स आहे. नेक्स्ट सायकल काय करते तर ह्या सिंक मधून QH2 अमाउंट ऑफ हीट घेते W2 अमाउंट ऑफ वर्क करते आणि QL2 अमाउंट ऑफ हीट लॉस करते त्याच्या सिंकला. Okay. Now here first thermal efficiency is given Q1. First efficiency is given, that is 30% or 0.3. Here its efficiency is given 0.2. They are asking what is the total or the overall efficiency. What is the overall efficiency? Now remember there is a formula for this. Actually there is very big derivation is there, but derivation is not relevant in this online mode. So directly I will tell you the formula. N overall will be equal to N1 plus N2 minus N1 into N2. Okay, so here it will be 0.3 plus 0.2 minus 0.3 into 0.2. So this will be what? 0.5 minus this will be 0.06 and this will be equal to 0.44, or we can say 44%. Okay, so option here, this option is right, option B. Now very important conclusion from this. हे बघा आता प्रत्येकाची एफिशियन्सी काय बघा तुम्ही किती ह्याची 0.3 0.2 आहे, पण ओव्हरऑल एफिशियन्सी तुमची 44% येते. म्हणजे काय, ज्यावेळेस तुम्ही दोन हीट इंजिन त्यांची एफिशियन्सी कमी का असेल ना, ते जर तुम्ही सिरीज मध्ये लावले तर त्या केसमध्ये काय होते, ओव्हरऑल एफिशियन्सी तुमची वाढत जाते. ओके, दिस इज द ब्युटी ऑफ कपलिंग हीट इंजिन्स इनटू सिरीज. ठीक आहे, म्हणजे त्यांची इंडिव्हिज्युअल एफिशियन्सी किती का कमी असेल ना, when you couple them in series their overall efficiency increases. Okay, again this is a MCQ type of examination. Example is there, they will give you these two efficiency and then they will tell you to calculate overall efficiency, so that time you should remember. So I think this is sufficient for D. How D is coming? How D is coming? Array Sudhir Rao, the formula is N1 plus N2 minus N1 into N2. So here it is 0.3 plus 0.2 minus 0.3 into 0.2. So what is 0.3 into 0.2? 0.06. 0.5 minus 0.06 is 4.44. So do your calculations, again you will get the answer. Okay, so with this we'll stop today. In next lecture again I will take some numericals and we'll start the important topic, that is entropy. Okay, we'll give a detailed explanation to entropy. We'll solve the numericals of the entropy also, and next two lectures our first chapter will be over. Okay, so please enter your roll numbers in the chat box and then we can stop. Enter only numbers, don't write anything SB or SA anything, just write your roll number. Yes, everybody, put your attendance in the chat box. Put your attendance in the chat box and then they can leave. Okay, so with this we'll stop today. Thank you for attending.